Swayam Prabha. Digital India. Educated India.
In the previous class, we started our discussion on momentum conservation for single particles. We have seen that in Maxey-Rayleigh model for a spherical particle at a low Reynolds number, apart from the conventional drag force, which is Stokes drag, there are many other terms appear. So apart from drag and gravity term, there are many other terms which influence the particle motion, and they include the force due to the undisturbed flow, then due to acceleration of the fluid, which itself comprises of two terms. One is virtual or apparent mass term, and the other one is the Béchet or history term. So the undisturbed flow, first of all, so in this case the gradient in pressure or shear stresses in the undisturbed flow basically contributes to a force on the particle as expressed by this expression. And here we see that this force is important when the mass of fluid displaced by the particle is important, and this happens when we have the density of the carrier phase and the dispersed phase comparable to each other, or the carrier phase density is much larger than the dispersed phase, for example in bubbly fluids. Then we discussed the steady state drag. By steady state drag, we refer to a condition where the fluid is not accelerating due to the particle motion. So if, let's say, you drop a steel ball in a liquid, then as it moves down, it causes acceleration of the surrounding fluid. But here we are assuming that there is no such acceleration, and the drag is due to the steady state drag, which basically depends on the relative velocity, where this parameter u refers to the velocity of the carrier phase where it is not disturbed. So here we are not considering u, for example, in the boundary layer, but outside the boundary layer. Okay. So for example, if in this case where the ball is dropping in the liquid velocity can be considered as 0 because the liquid is not moving, but in reality it is not true. The liquid, some of the liquid is actually moving. So this is the steady state drag. Although we have fraction forces which correspond to the gradient in the velocity profile of the carrier flow, however, this is often neglected because the particle size is much less than the length scale over which this gradient is significant. From Stokes solution, we can show that this drag is basically equal to 3 pi mu times the relative velocity times the size of the particle, and we can show that the coefficient of drag basically is equal to 24 by Re in this case, where the Reynolds number is actually much less than 1. So only for this case we can solve the Navier-Stokes equation after simplifying it, and we can show that the total drag, which consists of the form drag and the skin friction drag, that is equal to this. So the drag coefficient is 24 by Re, as we have used earlier also. Next, how do we correct Stokes drag? So there are various factors which influence the drag. So how do we account for that? For example, Reynolds number effect, the equation for the drag force that we have just discussed, that is valid only for low Reynolds number case. So what happens if we have high Reynolds number? So in that case we can introduce a correction factor to the coefficient of drag. So now various models are available depending on the range of the Reynolds number. Okay. So for example, here you see how the drag coefficient varies with Reynolds number. So when the Reynolds number is low, so in this zone you see that the Stokes drag and the actual drag are actually close to each other. Okay. However, as the Reynolds number increases, we see departure from the Stokes theory. So this line represents the Stokes theory. So this tells you that the actual drag is more than the Stokes drag. Okay. And the drag coefficient actually reduces with Reynolds number, and then it remains constant. So by this time we have turbulent boundary layer, and then we see a critical Reynolds number where the drag coefficient decreases and then it increases significantly. Now, for all practical purpose, we use a model similar to this one. So basically this tells you that the friction factor itself is a function of the Reynolds number, and it's a nonlinear function, and this expression is valid for, say, Reynolds number less than 800. But in practical case, we don't realize Reynolds number beyond this range mostly. Okay. And this is because of the particle size. Okay. Because the particle size is so small, that is why Reynolds number in where you have this kind of range is practically we don't encounter. Maybe let's say close to an injector exit, you may have some high value of Reynolds number because the droplet velocity is high, but otherwise not. So we can use similar model for the friction factor, and you see here how the drag factor or this correction factor varies with Reynolds number. So obviously when we have low Reynolds number, then this tends to be 1, but the value increases. I mean, this friction, this correction factor increases as we increase the Reynolds number. Now this is about the Reynolds number effect, but before we move on, it is important to look at this parameter known as terminal velocity. So what is terminal velocity? I am sure you would have encountered this earlier. So this is basically the final velocity attained by a particle when it falls in a quiescent fluid. So what is meant by final velocity? So if you consider a particle which is falling in a quiescent fluid, and the velocity of the carrier phase is 0, and one particle is simply falling under gravity. So now if we write the equation of motion, so in that case mass times the acceleration basically is equal to the drag force which is acting. So the particle is falling in this direction. So this is drag force which is opposite to its motion, and we have the gravitational force and also the buoyancy force. Okay. So then once the terminal velocity is achieved, then we have the acceleration term 0. So this is basically the definition of terminal velocity. When the velocity becomes constant, acceleration is 0. So putting this, we get this expression, and by simplifying here, we get that the terminal velocity is basically equal to g times tau d, which is nothing but the particle relaxation times divided by the correction factor times 1 minus rho c by rho d. If we assume that the carrier phase density is much less than the density of the particle, for example, we have liquid droplets in gaseous flow or solid particles in gaseous flow, then, and if the friction factor is close to, or the correction factor is close to 1, then what we get is this expression. That is, the terminal velocity is nothing but the product of the particle relaxation time and the acceleration due to gravity. So what is particle relaxation time or particle response time? It is the time that is required for a particle to get adjusted with the surrounding flow in terms of momentum transfer. Okay. So we can find the terminal velocity of a particle if we know its size, basically, because you calculate the particle relaxation time and multiply that with g. Now this is important because if we want to understand the role of gravity on particles, for example, let's say you have flow which carries some solid particle, let's say dust particles, and you want to study its behavior, then whether gravity is important or not, how will you quantify that? So if you compare, for example, a typical velocity of the particle with the terminal velocity, and if you find that the terminal velocity is much less than the velocity of the particle, then the effect of gravity can be neglected. But if they are comparable, then it is important. For example, sedimentation in river. So in that case, the gravity effect is definitely important. Okay. And if you remember, we use this only to calculate or to measure viscosity of a fluid in lab scale experiments. So you might have done this experiment where you take a long tube and fill it with some liquid, let's say oil, and you drop a steel ball. Then what you calculate is basically the terminal velocity, because once you know the terminal velocity, you can find what is the viscosity, because viscosity appears here. Next, there are various other factors which affects the drag force, or which influences the force on a particle, and we take that into account, as I said, by this correction factor. So we have seen that the correction factor for the drag coefficient depends on Reynolds number, but apart from Reynolds number, which other parameters influence this correction factor? That is what we are going to discuss. So if we get an appropriate expression for the correction factor, we can bring in, or we can take into account that effect. Okay. So first, effect of turbulence. So if a flow is turbulent, then the turbulence itself will affect the drag on a particle, which we didn't take into account in Stokes drag. Now the question is, under what condition the turbulence effect will be prominent? So there are basically two parameters which influence this. First one is relative turbulent intensity. So we'll discuss particle turbulence interaction somewhat later in this course in more detail. But if you see here, the parameters which influence the turbulence effect is, first one is, you compare the typical turbulent fluctuations. So you can consider u dash as the standard deviation of the velocity, let's say at any point. So that is your fluctuation, that represents the fluctuating velocity. And if you normalize that with the relative velocity between the particle and the carrier phase, which is basically, we call this as slip velocity also. So the relative magnitude of the velocity fluctuations, fluid velocity fluctuations, and the relative velocity. So obviously when this parameter is high, then the effect of turbulence is considerable. Then another important factor in case of turbulent flow is that you have a spectrum of length scales and time scales, which are basically corresponding to eddies of different size. You have large eddy, you have small eddy, and and the eddy size reduces. Okay, the smallest eddy is called Kolmogorov eddy. Okay, and the large eddies scales with the geometry of the flow. So now the ratio of the length scale of the eddy to the particle size is another parameter which also affects how turbulence would affect your flow. So if the particle size is much less than the smallest scale of the eddy, smallest length scale, eddy length scale, for example Kolmogorov scale, if the particle size is less than the Kolmogorov scale, so this means that the effect of turbulence might not be significant. But if the particle size is scaling with the large scale eddies of the flow, then you can have an effect. So for example, again, if we consider, let's say, a jet flow. So if you have particle size which is comparable to the radius of the jet, then the effect of turbulence will be significant. Okay. However, it is not straightforward, or there is no as such generic model which would describe this correction factor, okay, for all cases, because it depends also on the ratio of particle size to the eddy length scale. Next, non-spherical particles. So in many cases we may encounter non-spherical particles. So, and whatever expression for the drag coefficient we have, that is for spherical particle, we have to remember that. Okay. So if you have a non-spherical particle, then the question is how the drag coefficient differs. So we can account for that first of all by defining an equivalent diameter. What is an equivalent diameter? So you imagine you have a spherical particle which has same volume as the volume of this non-spherical particle. So that is the equivalent diameter. So you calculate the equivalent diameter, and then you may use this expression. Okay, so you calculate Reynolds number based on this equivalent diameter. And also the other parameter is the degree of non-sphericity. So you can do that as far as the degree of non-sphericity is close to unity. So what is degree of non-sphericity is how much it differs from a spherical particle. Let's say you have a particle something like this, a disc shaped particle. Then the straightforward use of Stokes drag, okay, will cause error. So you need appropriate correction factor for that. Next, particles may rotate also. So when they are transported by the carrier phase, the particles may rotate, and if they rotate, the question is, would it affect the drag or not? The answer is yes. Okay, and why is this so? Because it affects the boundary layer basically. But much less information is available on drag coefficient of spinning particles, and this is mainly because of the difficulty in measuring the drag coefficients and quantifying the spinning rate, so that you can validate the models. So that is the main problem. So we can define a non-dimensional spin rate. So by calculating this, what is the numerator? The numerator is the tangential velocity of the particle at its surface. So if a particle rotates, then this is the tangential velocity r omega at the surface of the particle. So if we compare that with the slip velocity, and if this parameter is comparable to 1, or it is of the order of 1 or more than that, then we have to account for the particle rotation. So in this case, the correction factor will be a function of this non-dimensional number also. Then another interesting effect is the blowing effect. So now you imagine you have a particle which and where some mass transfer is taking place. For example, evaporating droplet. So here you have the vapor which is actually blowing out, and now you have a flow here. The question is, should the drag coefficient be same even if you have Stokes drag law valid or Stokes regime valid? The answer is no again, because this blowing effect will try to reduce the drag coefficient. Same is true, for example, if you have a burning droplet. So a burning droplet moving in ambience. Okay. So in that case also, the drag coefficient will differ from the case where you have a particle of similar size but without any burning or evaporation. And this can be accounted. So this is again one model. These are not universal. So I mean, for validity of this model, means you need to apply it for certain conditions only. Okay. So this is a simple model which tells you that the drag coefficient reduces because of the evaporation or vaporization of the droplet. And here B is the transfer number that we have already discussed. So if you have let's say a droplet which is vaporizing in air, then you can use, for example, this expression. Okay, we have already discussed this transfer number. So here this refers to the thermal transfer number. So in this case, the drag coefficient decreases. But now let's say you have and this expression is also used for when you have a droplet which is burning. So you have a flame around this droplet. Okay. However, if you see, fundamentally it is different, because here you have a flame around the droplet. Okay. The way the flame influences the local flow field is not accounted in this model. So the point is that yes, on all these effects people have done research and they came up with some models, but these are not generic models. You can use it under certain conditions that we have to keep in mind. Next, we have also particle cloud effect. Again, for this we have very little information available. In all practical cases, you know that there are neighboring particles around any particle in the flow. So, and this effect is not accounted again in the Stokes theory. So if you have, let's say, these particles present, they will modify the local flow field. So the local flow field, now let's say this is your test particle. So the local flow field itself, or U, is modified because of the presence of other particles. So the question is, how far Stokes drag law is valid? Okay. So this is something similar to the group effect that we discussed in case of mass transfer from droplets. So if there are nearby droplets, they will definitely influence the rate of mass transfer. So similarly in this case. Now, development of analytical models are challenging, basically because the model must account for the disturbance created by each particle at its surface. And the experimental studies are also difficult because of the difficulty in measuring the force and the local flow field of an individual particle. Okay. So, but we often encounter this, for example, in fluidized beds. In fluidized beds, we have already discussed, so the volume fraction is quite high. So, the flow is definitely affected because of the presence of other particles, and in fact that only causes the overall pressure drop across your bed. Okay, but right now some or other models are available which accounts for these effects, and this is incorporated with the Stokes-Drag law. However, that is one way of modeling this effect. That is not the only way, but one simple way of accounting for all these effects in Stokes-Drag law. Okay, so now we'll look at another effect on particle motion, that is virtual or apparent mass effect. So what is that? So now we will consider the acceleration in the fluid due to the particle. So when a particle moves in a fluid, part of the fluid is accelerated along with the particle. So it is like the because of this acceleration. Now what causes this acceleration? Particle only. So this means that the particle has to put more work to accelerate the fluid. This means that it is exerting some force on the fluid. So according to Newton's third law, so that force must be acting on the particle also, and that is what is known as the virtual or apparent mass effect. So this force on the particle is basically proportional to the relative acceleration between the particle and the fluid. So now we have to consider the acceleration due to the acceleration of the particle as well as acceleration in the fluid. So earlier that effect was not there. Okay. So we didn't consider, for example, in Stokes-Drag law, we didn't consider the acceleration in the fluid. The relative velocity can change. Again, for example, let's say you have a stagnant flow and a particle is moving. Now you imagine you inject the particle at certain velocity, so it will stop after some time. So during this, the relative velocity changes. Relative velocity is basically u minus v. U is 0, so v is decreasing. This means that the relative velocity is changing. But here we are not accounting for the acceleration due to the particle, acceleration in the fluid due to the particle. Part of the fluid is also accelerating. Okay, so that is basically causing this force, and it can be shown. So without doing a derivation, I am only giving that direct expression for this force, which is known as the virtual mass effect. This is equal to this constant times rho f times Vd. Vd is the volume of the particle. So rho f Vd is basically the fluid mass displaced by the particle, and here we have the relative acceleration between the two phases. So for a sphere, this constant is about 0.5. Now it is obvious that this force is dominant when the particle and fluid densities are comparable again. For example, bubbly flow. So in that case, the fluid mass displaced by the particle is non-negligible because of the higher density of the carrier phase basically. So in that case, we have to account for this effect. We cannot only live with the Stokes-Drag law, or even a correction after incorporating correction to the Stokes-Drag law. It is not enough. We have to account for these effects such as virtual mass effect, and we have to remember that this is purely inertial effect, or it's like an added mass or added inertia on the particle. So you can imagine it like this, that instead of the particle mass, we have particle mass plus some added mass, and now that is moving, and that is why we have this extra force on the particle. That is why this is also known as apparent mass or added mass effect. So in a strict sense, here we don't have actually drag force. This is not a drag force which is caused due to the formation of the boundary layer. Rather, this is the virtual or apparent mass effect. Now the next one is the Bassett force. So now this is also a very interesting effect. So this refers to the temporal delay in boundary layer development as the relative velocity changes with time. So to understand this, we need to first look at the case where a flat plate is impulsively accelerated. This is also known as Stokes problem. So you imagine here you have a flat plate and there is a fluid on top of that, and the plate is suddenly accelerated. So we want to know what would be the shear stress on the plate. So that is the objective. So if we write down the Navier-Stokes equation, then we can do some simplification to this. Mainly we can drop the inertia term because we have suddenly pulled the plate. So the fluid inertia is not significant. So we have dropped those terms, and we here assume that the flow is varying mostly in y direction. Okay. So then we can simplify the Navier-Stokes equation with these initial conditions. So here at time t is equal to 0, we have the plate at rest, which is, so the velocity is 0. But for all time instant at y is equal to 0, that is on the plate, you have velocity equal to u naught. So u naught is the initial velocity, or this is the velocity at which you are dragging the plate, and ut infinity is 0, that is far away from the particle, you have 0 velocity. Okay. So we can solve this analytically, and here we see that the expression we get for the flow velocity is equal to this. So here this term eta basically depends on time and space, and once we know the velocity, then we can easily calculate the shear stress. Okay, that is rate of change of the velocity at the surface. Now if we do that, we get this term. Now this refers to the instantaneous shear stress, and what is interesting is this term T here. That is, now shear stress depends on time also. Now if I want to calculate the shear stress on the plate starting from time t is equal to 0 to some time, then I will have to integrate this equation from 0 till that time. So if we do that, we get this expression. So what does this tell you? This tells you that the shear stress at any point of time, okay, on the plate, the time integrated shear stress is basically dependent on the history of the flow. It depends. So this is basically the history term. So what has already happened, that influences the shear stress, your shear stress now. Okay, is it clear? So you have dragged the plate, okay, and let's say you are dragging for 5 seconds. Then the shear stress at 5th second or at 5 second instant depends on the fluid behavior at 1 second also. So that is why it is known as history term. And interestingly, this scientist Bassett used the same approach to calculate the history effect for a particle. So now you imagine instead of a flat plate you have a particle, and he calculated the Bassett history term. So you see the similarity between these two, but here again this depends on the relative velocity between the two phases, or the time variation of, or the time signature of the relative velocity would also influence the would basically influence the Bassett term. Okay, so this represents a drag term. Now here we are talking about the drag due to the boundary layer basically. Now we can compare this with the particle inertial force and see how significant it is, or under what condition Bassett force is significant compared to the particle inertia. So we can compare this with mass times acceleration, and it is possible to show that this ratio is basically equal to the ratio between the fluid and the particle, and diameter, it varies inversely with the diameter, and obviously it has dependence on the viscosity. This is the kinematic viscosity. So higher the viscosity, higher is the effect as expected. But what is interesting is this. So here again we see that this will be important when the fluid density is comparable to the density of the particle, and also when the particle size is really very small. Okay, so the history force is negligible when we have heavier particles in a fluid, or fluid density or fluid is lighter than the particle. So now in this case what happens is that the particle's inertia is so dominant that the unsteady viscous boundary layer cannot significantly alter its motion. So under this condition basically, so when we have heavier particles in the fluid, the inertial force dominant over this history term. That is why it can be safely neglected. But again, if you consider flows such as bubbly flows, then, or even flows where we have liquid and particle density comparable, let's say solid particles in liquid flow. So there also the history term can be important. Okay, so there are forces other than drag force. So till now what we considered are mainly the forces due to drag, and what we see from, and that's what we see from Maxey-Rayleigh model. But there are other forces which are possible on a particle, and one such force is Safman lift force. What it is? So basically when we have a small particle which moving through a shear flow means you have a strong velocity gradient in the flow, then it experiences sideway force perpendicular to the relative velocity. Okay, when we have Stokes flow region. So Stokes flow didn't take or Stokes theory didn't take into account this effect. However, because in that case the particle was kept under uniform flow, but if you have a shear flow, okay, then it is possible that the particle will get a force in this direction. Okay, that is perpendicular to the relative velocity. Okay, now this force basically arises because the particle disturbs the shear flow asymmetrically, leading to an imbalance in pressure and viscous stresses around the particle. And it can be shown that this lift force, which was first discovered by the scientist named Safman, so this Safman lift force is again proportional to the relative velocity between the particle, and also you have this term where you have square root of shear Reynolds number, where shear Reynolds number is given by this expression. Okay. So here, that's how you consider the, you account for the gradient in the velocity. Now, also we can show that this lift force depends on the cross product between the slip velocity and fluid vorticity. So this is how you determine the direction of the Shaftman lift force. It's called lift force, but it's not like its direction is always in the positive y direction. Okay. Now, if the relative velocity is positive, there is a lift force towards higher velocity of the continuous phase and vice versa. So, for example, dusts in boundary layer. So, the dust particles moving close to the wall get pushed sideways due to shear affecting deposition. So, imagine dusty flow close to the boundary. Why close to the boundary? Because there only you will see strong gradient in the fluid velocity due to boundary layer. So, in that case, the particles can move sideways because of this gradient, because of the Shaftman lift force. And also the other example is blood cells in arteries, where the shear induced lift pushes red blood cells away from the vessel wall. So obviously in such flows where you have, for example, blood flow in artery, the boundary layer effect is always significant due to the dimension of the flow. So there we can encounter such forces. Another example is Magnus force. So you are all familiar with Magnus force if you have interest in cricket. So when you have, especially the spinners, so they spin the ball, and or say even in tennis ball also, so they hit the ball such that it spins. So when the ball spins, it is possible that a force act on it and it can influence its trajectory. So even if initially the velocity is in some direction, its trajectory can change, and this is known as the Magnus effect. So this happens because of pressure differential between both sides of the particle, okay, because of the rotation of the particle. And in this case, the Magnus force can be expressed through this form. So here you see that this depends on the cross product between slip velocity and the angular speed of the particle. So we can have these effects as well on a particle. Now, so there are other forces here also. So this should be now here we are not considering the drag force, but here now we are considering the angular momentum of the particle. So till now, whatever we have discussed, the forces, that is referring to the linear momentum exchange between the particle and the fluid phase. But we can have angular momentum exchange also. So in this case, the fluid flow would cause the particle to rotate. So here the particle's rotation basically interacts with the surrounding fluid flow and vice versa. So in this case, we need to consider the torque on a particle instead of force. So here I is the moment of inertia, and this is the rate of change of the angular velocity of the particle. This is very much analogous to the linear momentum coupling. So here this is basically equal to the torque, and for under steady state condition, this is given by this expression where it depends on the viscosity of the fluid, particle size and the angular velocity. But this is under steady state condition only. So it is also possible to show that for this case, for angular momentum exchange between the particle and fluid, we can have an expression very similar to Maxirelli equation of motion. So in this case also you can have contribution due to undisturbed flow and contributions due to virtual mass effect as well as the Bassett history term. Okay. For simplification, we haven't considered those. Now we move to energy conservation. So we have considered mass and momentum conservation for a single particle flow. Now we will look at the energy conservation. So again, we go back to the Reynolds transport theorem. So in this case, what is this parameter beta? This is basically equal to internal energy plus the kinetic energy. And we can show that the rate of change of energy of the system is equal to the rate of change of, or the rate of heat transfer minus work transfer. Where this is, so this is heat transfer rate, convective and radiative heat transfer, and here we have work transfer rate by the particle. So here we are basically considering the efflux of fluid through the control surface plus work associated with the forces on the droplet. So we know that the particle is doing, a particle is experiencing some force from the fluid. Particle is also exerting some force on the fluid. So we will have also work done possible because of the force. Okay, it can be due to drag force, it can be due to body force also. So the work done due to the force on the particle, that's what we are considering here. And here this is the heat transfer effect. But by assuming that we don't have particle rotation, internal motion within particles is negligible, kinetic energy associated with the efflux of the efflux velocity, that is in case of, let's say, droplet evaporation, the vapors leave the droplet with certain kinetic energy. But if we neglect that, okay, so if we neglect those, then it is possible to simplify the energy equation, and finally we can express it as this form. So here you have mCp times rate of change of temperature of the particle is equal to the convective effect plus the radiative effect plus the effect due to mass transfer. Okay. And we can always express the heat transfer coefficient in terms of Nusselt number. So we can basically replace heat transfer coefficient with the Nusselt number, and the Nusselt number is given by this correlation. However, this correlation is also applicable under certain conditions. Okay, but usually we use this Range-Marshall correlation. You have encountered this correlation earlier in the context of mass transfer when we discussed. Okay. So finally, we have now all the single particle equations summarized. So in summary, we have, this is the mass conservation equation for a single particle, and here we used the d-square law model to calculate the rate of change of mass of a particle, which basically depends on the particle size and the transfer number. Okay, where here I am writing mass transfer number, which is obtained like this, where the vapor mass fraction at the particle surface can be obtained from Clausius-Clapeyron equation. And we have also discussed that similar expression is possible from energy transfer analysis, and in that case we have thermal transfer number Bt, and the d-square law basically implies this equation, this simple equation, that the rate of change of particle surface area is constant. So basically these two expressions are equivalent, where this is the evaporation constant or vaporization constant. So we can express also kV in terms of the thermal transfer number, and in that case instead of Sherwood number we will have Nusselt number. Same Nusselt number expression. So you see it is basically same. Then here I have written the simplified momentum conservation equation, that is mass times acceleration is equal to the Stokes drag term multiplied with some correction factor plus g. Okay, here I haven't considered the other terms, okay, in the Maxian-Rayleigh equation, like undisturbed term, then fluid acceleration term I have neglected, and then this is the energy conservation equation. Okay, so with this now we are ready to do some analysis in particle laden flows, where we can predict the particle behavior when the carrier phase is prescribed. So we don't have to bother about carrier phase because it is prescribed, but we can study the behavior of particles, and that is what we will do in the next class. Thank you.